Good afternoon, everyone, and welcome to another great weekly webinar hosted by the Connecticut Center for Advanced Technology and really put together and spearheaded by the New England Regional Defense Industry Collaboration, Nerdic. I'm going to get into that a little bit and explain to you what Nerdic is. Many of you probably on the line know by now, but we've got a great program. I'm going to give some brief introductions, and as you can see up on the screen, we're going to have Kathy Mahoney come on. She is the Center Director for Polaris MEP in Rhode Island. We've got a great presentation team. Today's title, when you look at Generative Design and Additive Manufacturing, it's something that we've talked about over the past year or two, and we're going to be continuing to talk about it. It's not something that we can just kind of do a snapshot in time. It's one of these things that, as we look at technology adoption, technology advancement, it's going to be very, very critical for our supply chain companies to get on board with this, to be able to understand this technology. So you're going to hear a lot about it. But to give you a little brief overview of Nerdic, again, the New England Regional Defense Industry Collaboration. We've talked a lot, even probably over the past decade, about how do we come together as a region and really show a lot more power, a lot more might to what we have here in this region. And Nerdic has been that key. We've got representatives from all the different states coming in. We've got the MEPs and the PTAPs there. We've got educational institutions, we've got industry, and all of them are around or form this ecosystem around Nerdic, which is really the convener of this group. And if we could start talking more holistically when we talk about technology, talk about best practices, and certainly when we talk about education, workforce development, training, it's one of those things where we really have to look at what we're doing New England based, because our big defense contractors, they just don't reside in any one state. What they're doing really branches out through all the states, not just throughout the country, but really what we're looking at here in New England. And of course, off to that side, you see that column there, we're really focusing on those Industry 4.0 technologies. The things around, even today, when we talk about generative design and additive, but of course, there's automation. There's things around augmented reality. There's cybersecurity that comes into play, and some of the other things below. So a lot of great topics that we're going to continue to bring, and Nerdic is going to be that real group that's kind of pulling everybody together. So at this time, I'd like to bring on Kathy Mahoney. You see Kathy again, she's the director of Polaris MEP. But we have all the MEPs here throughout New England coming together. And Kathy, the importance of the MEP network, can never be overstated. So important. You guys are that front line of defense. You're always bringing these great programs, things that are pulling our supply chain forward, those small companies. Today's an important topic, but there's a lot of others. So, I'd love to hear a few of your topics today, comments.
Thanks, Ron. So we're the MEP Center representing Rhode Island. There's an MEP Center in every state, as you can see from the New England states listed below. And geographically, we all know that supply chains and employees don't end at state lines. So we all work very closely together to make sure that there's a workforce and that we're addressing the trends within manufacturing. And Nerdic is a perfect example of that. All of the New England centers are working to make sure that our client companies have the Industry 4.0 readiness and the training programs that they need, as well as the information to help them grow and improve. And these webinars that CCAT is putting on is a great example of that. So we're thrilled to be here and a part of this, and excited to see what the next generation of manufacturing is. In Rhode Island in particular, we are working on a training program, building a training facility that will be launched in the summer of 2022. And additive manufacturing is slated to be part of phase 2 of that program. So we're looking forward to hearing what everyone has to say, and the questions and answers conversations that happen afterwards are always my favorite part.
Well, Kathy, thank you for that. That training facility is going to be real interesting, because how do we leverage that? That's going to be an important asset, not just for Rhode Island, as you said. These supply chains cross all the lines, so we're all going to be interested in some of the program. And I suspect maybe we'll have some webinars, coming out of that training center. So it's just going to be a great addition, great tool in the toolbox that we have.
I agree, and part of that, we're actually planning a field trip with the Polaris staff to come down to CCAT and check you guys out, so we can learn from all the best practices that you have.
And hopefully a lot of the mistakes that we've made over the past decade, we won't repeat any of those, but it is a learning process. And,
yep.
With that facility, we've got the Berkshire Innovation Center and the interesting things going on in the other states, how those things are connected in kind of a holistic way. How do we leverage each other? it's really we've got a supply chain that just is completely linked. So the more we can be doing together, the better. So it's great to have you on. I know you got great things coming out of Rhode Island. We're going to hear a lot more of them going forward. But thank you for your time and your comments today.
Thank you for having me.
Great. So now we'll bring on, I think the first person we're going to bring on is Nasir Manin. Now Nasir is one of our engineers, our principal engineer at CCAT, and he basically oversees our advanced design, automation, metrology area. A lot going on. Nasir, you're probably one of the folks that has got your plate, overflowing. You've probably got a whole bunch of plates overflowing. But this has been a great topic for you. I know we've got some other panelists. We got Jeff Crandall, we've got Sam Greenbank coming on, and Chris Coulter and Jonathan Bicknell. You can bring them on as you'd like. I know you've got a great program. Your presentations are always fantastic. So I'm looking forward to it. And for everyone on this, there's going to be handouts on this. We'll supply you with the whole presentation. If you've got any interesting questions for Nasir, you can put those into the chat area, and Nasir will address those when he finishes up. So we'll hand it off to you, Nasir.
How do I put this on?
Thanks, Ron. I appreciate it. So I'm at this point, I'm going to invite my colleague Jeff Crandall to come on, and we'll follow that up with my other colleague Sam Greenback, who will talk about some of the the printing process, and then I'll come on to talk about some of the results of the printing stuff. So Jeff, I'll hand it off to you.
All right, thank you, Nasir. Yeah, Nasir asked before we get started on this, just for a really quick recap on the technology and the additive industry. So, first, by definition, what is it? It's an Industry 4.0 technology. It's one of the 9 categories. It involves using a 3D digital model, and you break that down and you build a part one layer at a time, and you add material where you need it. Next slide, please. So what's the benefits of that versus other traditional methods? It has the potential to make things better, faster, cheaper, lighter than some of the conventional technologies. Early adopters in the aerospace industry are reporting as much as a 90% savings or reduction in material cost. They're not creating the scrap and the waste that they do in some of the traditional processes as far as metals go. With the new tools that are available for topology optimization and generative design, it's being used to help lightweight parts. So here again, in the aerospace and electric automotive and many different industries, that's an important feature. It's great for part consolidation. So once again, when we look at trying to make, instead of multiple parts conventionally, where we're limited on how they can be made using additive technology, we're making parts out of a single piece as a single piece now. So the fuel nozzle from GE's LEAP engine is a great example. It was 20 plus parts originally the way it was designed and manufactured. They're building it now additively as a single part. So next slide, please. So why use AM? Once again, it can be a tool to create things that are difficult or even impossible to do with other technologies. So if we look on the left, the heat exchanger, you have a helix inside a tube. This would be impossible to build as a single piece anyway using conventional tools. You can design for end use versus manufacturer. So when you design something, hopefully it's designed to be manufactured, and there's limitations on how you can hold it, how you can build it, what you can do inside the mold, et cetera, et cetera. Using additive technologies helps to free up some of the design constraints that were traditionally met. So the concept of free complexity. So when we look at the matrix in the middle, this is a great example where this would be impossible to build using conventional technologies, but it's really more hard to build using additive technology as building a solid cube. Next, please. So Typically, there's no tooling or fixturing involved. So when you're looking at the low to mid volume production range, if you don't have to have molds or dies made, this can be a tremendous savings. So when we look at the electrical connector on the right, that's made using additive technology, and it has as good characteristics as something that's traditionally injection molded. The idea of mass customization. So if we look at the tooth inserts in the middle photograph, each one of these is built for a specific patient, and they're all built simultaneously on the same build plate. So the idea of making multiple parts simultaneously, each one different from the others. And once again, it's ideal for low to mid volume production, which that could mean one up, or it could mean thousands or even tens of thousands of a part. So, when we look at some of the keys in the additive industry, it is rapidly evolving as a mainstream manufacturing tool. It is just one, it's a subset of tools of all of the tools that are available to manufacturers today. And when you look at additive, it's not just a single technology or a single piece of equipment, but it's a family of technologies, and they truly can be and are being applied to almost every industry sector and every business size. So when we look at the ASTM F42 committee, has defined 7 different areas of additive or technology families that comprise additive plus hybrid. So there's a lot of different technologies available. Once again, a lot of different kinds of tools in the tool set. Depending on what you want to do, one or more of these tools may be more appropriate than others. So that's outside of the conversation of this presentation. So when you look at the types of materials, so basically anything that's made using conventional technologies can more than likely be made using additive technology. So a full range of plastics and polymers, full range of metals, composite materials, ceramics, and even sand. So the printing of digital printing of molds and cores for the casting industry. And key is that new materials are rapidly being developed specifically for the additive process. And in fact, they're being customized for the additive process. So it's getting to the point where you can, tell a company that you need a part that has to meet these specifications, and if there's not an existing material, it's possible to custom design a material for that application. So, additive is being used in a multitude of industries for producing new parts. So this is a wide range of some of the things that are possible. Next slide, please. But what we see as a low-hanging fruit, or something that is very commonly used, excuse me, for additive today, is aids to manufacturing. So the idea originally of additive manufacturing, it was a tremendous tool for prototyping. So it greatly speeds up, or continues to speed up, the design process. So people are using it, to produce models so that they can visualize a complex part, what they need to do to fixture it conventionally, or they can even begin making test cuts and begin developing their process while they're waiting, as an example, for casting to come in. And people affectionately are starting to refer to it as a 21st century duct tape. So there's not much that you can't do with it. As we continue to talk about aids to manufacturing, the idea of, fixtures, jigs, guides, customized tool carriers, customized parts trays for assembly, just a wide range of applications. Once again, with all of the materials that are available, if you can conceive it and you can build it conventionally, then here again, additive might be a great tool. It's freeing up as a means for creating fixture. It's reducing the cost of building those fixtures. It's reducing the time required to build them. And so it's really revolutionizing the use and availability of fixtures. Right, next, please. So the takeaways in quick summary is additives here to stay. It's not a flavor of the month. It's a very real manufacturing tool that's moving rapidly into manufacturing mainstream. It's evolving and it's being adopted at a much faster rate than many companies realize. So if you're not using additive today, it would be an interesting experience for you to realize your competitors and other industries that are adopting it and making use of it. The materials are evolving, and as the materials are evolving, also are the design and the modeling tools. So it truly is enabling and allowing people to build new parts in new ways. It's, here again, repeat, it is rapidly becoming a mainstream manufacturing tool. It can work synergistically with traditional technology. So once again, the idea of, additive and traditional, subtractive machining, working on a lathe, cutting, grinding are all, technologies that work hand in hand with each other. And it won't completely replace traditional manufacturing tools, but it is going to be highly disruptive. So there's a lot of companies that have already adopted it, and a lot of OEMs are investing heavily in it. So I think that's all I have. So if there's any questions when we have questions and answers, I'll be available, and I'll turn it over to Nasir.
You got some.
Thanks, Jeff. So now we're going to get into some of the case studies. We did two case studies. The first one was with Concepts NREC. And I'm going to invite my colleague, Sam Greenbank, to come on and talk about the actual building process.
Hello. So just to kind of go over this part and what we did with it. We were given a part and really tasked with validating how manufacturable the part is using additive technologies to really look at how easy is it to make, can it be made, what kind of things are there to watch out for, how well does it meet tolerance, being made, etc. The part is fairly complex. It has internal channels that could not be conventionally manufactured.
Yeah.
We used a Renishaw AM400 to build the part to powder bed fusion machine, and we used 316L stainless steel powder for the build. Namely, that's what we have on hand, and it's a good material to work with for validation before using more expensive end-use materials. Total print time was about 36 hours. Actually in machine running time, and the total time to program the machine, any maintenance of the machine while it was running, and then cleaning up and post-processing. Initial work, there's still, we didn't do a complete post-processing job, as you'll see in a moment, but the total time up until the point where we have it now is about 5 hours worth of labor. So to kind of go over the initial issues that we saw is the part geometry itself posed several challenges. The part had a fairly large area of overhang that would not be in direct contact with the build plate. That was at a very shallow angle that's prone to lifting and peeling without adequate supports and tie downs. Several of the internal cavities also had a flat roof, for lack of a better term, that again is also would typically need support material. However, being that it's an internal cavity, supports would not be removable. So that was an area of concern, and part of the reason that we were wanting to validate this part first before going much further with it. To the strategies I used to print this part is I printed two parts side by side. The first one was using traditional pillared support material, basically a bunch of posts on the bottom surface of the part, tying it down to the build plate. My my concern was that this would rip free of the supports, and the surface finish of the bottom surface would not be adequate, and there wouldn't be enough material left to post machine if the surface finish was not adequate. So then on the second part, I did an extruded bottom. I basically flattened out the bottom and dropped it all the way down to the build plate as one solid piece. The other major problem that was encountered is removing the powder from the internal passages. There's very small holes to clear that out. You'll see that in a second. And a fairly large volume of powder inside the cavities. So removing that is definitely a challenge, and it's one of the requirements of post-processing that is often overlooked. And in this case, both parts will need to be finished machined to meet some of the specifications. And there will be some corrections that will probably need to be done in the model before printing further sets. Go on to the next slide. So this is an overview of the part. It's a turbine blade. The top left is the outside of the part. There's two different cutaways immediately to the right of that. The top one is the part as designed, and the one on the bottom is where I extruded the bottom out to give it a flat surface to build on, as opposed to using pillars to support the part. Then in the bottom left is a picture of the internal channels rendered as solid, with the outside of the part being rendered as transparent. So you kind of have an idea of how the part, how large the channels are, and that volume of powder essentially needs to be removed after the build. On the right-hand side of the screen, we have the setup of the software in the Renishaw software to build the part. First one is the layout with the supports, and then the other one is the toolpath validation. And finally, the bottom picture on the right side is a shot of the machine running to kind of see how the parts were nested together in the powder build. Go to the next, please. So this is the finished part coming out. Surface finish, and the fact that it completed without any real issues was a bit more than what I personally expected from the part. I expected to have more difficulties than we did have. The build plate did warp significantly and required quite a bit of work to get it out of the machine. The other issue that we had is the holes that you can see in the center picture, cooling holes. Those are about a 0.5 millimeter in diameter on the model. Some of those towards the end collapsed a little bit in size. And so to clean those out, we used a microblaster to open up the holes slightly, and then that allowed, removed any collapsed material from in there, and then that allowed us to remove the material on the powder from inside the blades by using the same microblaster without the blast media to blow air through the cavities to flush the powder out those holes. And you can also see on the right side the two small holes also on the top of the blades. Again, something that would be quite difficult to manufacture in traditional means. Next slide. So, this is an inspection. I'll turn it back over to Nasir to go over the inspection and the results.
Thanks, Sam. So at this point, we're going to get into the post kind of analysis on, we took some scans of the parts so that we can get some dimensional information. What was the distortion from the as compared to the original CAD design? And then also some CT scans as well, and X-ray images. So what we're going to do is I'm going to intermittently bring on my colleagues to comment, but I'll just go through. I'm going to turn off my video so that some of I think it gives you a little bit more real estate to view the slides. Some of the text on there came out a little small, so I'm going to go ahead and turn that off. Basically, what you saw on the previous slide was the setup on the GOM structure-like scanning system. You see on the left there, that red component on the robot is the actual sensor. It uses a structure-like pattern to scan the part. And what we do is, with this kind of non-contact inspection system, the image in the center is, you see the part, it's just placed on a few standoffs, and it's placed within a cage that has a bunch of dots on it, and those dots are called photogrammetry dots. They're used by the scanning system to track the location of that part as it's being moved around, and as the robot is moving the sensor around the part for the alignment of the individual scans. And so the picture on the right, you see it in action. There's a blue light projected on to the surface of the part. A structural light pattern, is projected on, and it deforms as it hits the surface, and cameras take images of that deformed pattern to reconstruct the surface. Next slide, please. So what you see here is the CAD model and the scan data aligned to that CAD model. And the alignment here is by best fit. That's really the best way I'm going to be able to see the comparison of the two different files that Sam had printed out. On the left, you see the file or the part with the that matched the curvature at the bottom of the part, and then the extruded flat bottom on the right. Next slide, please. So some quick visuals. If we zoom in on some areas at the top there, that top cylinder feature, you can see that the scan data is below the surface. So we're going to expect to see a negative deviation there. And on the picture at the bottom left and the bottom right, you can see the respective tips of the impeller blades. You can see the picture on the left where it did not have an extruded flat bottom. Sam mentioned earlier, there was a little bit of a warpage of the part right at the tip, and it warped upwards, which pulled the surface that the four cooling holes are on the tip away. So we should see a negative deviation at the bottom, and we should see and also a negative deviation on the tips. So here, what we're looking at, these two images represent a coloration of the of the difference between the surface of the CAD model and the actual scanned part. The red indicates where the physical part has too much material, and as you get down into the blue, we get into areas of where the actual surface of the part is below the CAD surface. So what you can see in the image on the left is pretty consistently, we're seeing that the impeller blades have on the suction side, you're seeing a positive deviation. In other words, there's too much material. And then you can see on the left blades, kind of on the bottom surface on the pressure side, there is a negative deviation. So what that's indicating is that the actual surface is more curved than the CAD file than the design in the CAD file. Similarly, you can see on the on the deviation map on the left there for the curved bottom surface part, right at the tips, at the base of the tips of the impeller blades, you see red, and that's indicating that that surface, the physical part has more material there. In other words, it's curled upwards. And we'll see, we'll take some measurements there to show you exactly how much that is. On the right though, what you can see with the extruded flat bottom is that we have a little bit less curvature, less deformation holistically on the part. we still have more material, more of a curvature of the impeller blade, as indicated by the positive deviation on the suction side and the negative deviation on the pressure side. And then on the tips of the, you see that the positive deviation there is less. It's not as red, it's more in the orange area. And so we're seeing much less deformation on the bottom of that part, and that was due to that flat bottom that Sam had extruded down. So overall, the takeaway here in this image is that you know, preparing the bottom of the part to have as much a surface area in contact with the build plate help to overall minimize distortion of the part. Next slide, please. So here's another image of the bottom here. This is probably, it's less important to see the image on the right because we know we're gonna have positive deviation there because of the extruded flat. But the image on the left is, you know, the original design of the file as it was printed. You can see that towards the hole at the bottom in the center of the part, there is a positive deviation there. It means that we have a lot of material. And as we go towards the tip, you see it transition over to blue, which is telling us that it goes from the physical part having too much material in the center and having less and less material until it actually doesn't have enough. It's actually in the surfaces above the CAD surface. So we're seeing a overall even, if you can say, a bowl distortion at the bottom of that part. Next image, please. So here we're getting into some of the, you know, the actual measurements. And so we're keeping with, you know, comparing the curved bottom surface part with the extruded flat bottom on the right. You can see that the deviation on the curved bottom surface part file was more. So you see that the positive deviation on the suction side of the impeller blade right there in the center is about 17 thousandths, whereas it's about 13 thousandths on the extruded flat bottom part. If you go further down, you see that the deviation goes to 10,000 and then to about 8,000 on the flat bottom part. So we're seeing overall less of a curvature deviation on the blade. And then as we get to the kind of the if you will, the end of the tip of the blade there, we're seeing about the same deviation there. So we're seeing about 2 thousandths down to about 5 thousandths. So overall, you know, again, the order of, you know, we're looking at a good, you know, 5 thousandths less deviation on the curvature of that blade. So on the pressure side, again, we're seeing a similar pattern here. We're seeing about 19 thousandths at its most negative deviation on the curved bottom surface. On the extruded flat bottom, we're only seeing 16. So we're about 3 thousandths less in deviation there. And then again, as we go down, we're about 4 thousandths at that next point on the curved bottom surface, as opposed to only 2 thousandths, so about 2 thousandths less. So what this is indicating is that, again, because the deviation is about the same for the pressure and the suction side in terms of the deviation, the thickness of the blade is maintained, but the overall curvature of that blade is changed. So that's the takeaway here between the first and the second image that we saw. Next slide, please. So here, right about where the maximum deviation is for that blade, we took a cross section, and we're looking at a whisker plot of the section, and the whisker plot is it's exaggerated by a multiplication factor. So it's not, the physical part isn't this much off. It's I think I multiplied it by a factor of 10. but the numbers there are indicating the actual value of the deviation. But what this is showing is the consistent thickness and the curvature deviation. So this is indicating an overall warpage, of the part. But the order of magnitude is about 20 thousandths of maximum curvature deviation. On the curved bottom surface. On the extruded flat bottom, we're only looking at about, it's about, the average would be about 15 thousandths versus the 20 thousandths that was on the curved bottom surface. Next slide, please. Again, this is another cross section, but from a different, that was along the Z-axis. This is along the Y-axis. And again, you're seeing the same thing, just an overall curvature. Overall, we're seeing again about 18 thousandths on the curved bottom surface, but only about 12 thousandths on the extruded flat bottom part. Next slide, please. The top surface, you can see here, we're actually shorter. There's less material on the part that was designed with the flat bottom part. So we're about 10 thousandths there on the top cylinder face, but only negative 7 thousandths on the curved bottom surface. Again, here, this is just showing the values of the of how that bottom surface is warped. So the image that's probably the most, the one that's the most telling is the image on the left, where we're at about a positive deviation of 31 thousandths near the bottom hole. And as we go out to the tip of the impeller blade, we go from a positive deviation of 31 to a positive deviation of 15, then almost nominal at about 3 thousandths in the middle. And then we start going negative 4 thousandths and then 26 thousandths towards the edge. So you see that the curvature becomes more exaggerated as you go out to the tip, which probably has overall less, less material than the bulk that's in the center. The image on the right is not really going to tell us much because we had an extruded flat bottom. So overall, we know that we're going to have a positive deviation there. So by comparison, we're just looking at the left image. This is a cross section of the top cylinder feature of the impeller. And what's interesting here is that you can see that the deviation of the top cylinder on the actual part is towards the left overall. I mean, the center, the holes are not, the hole is not concentric to the outer cylinder because it deviates more than what we find. So it's a little bit of a thinner wall on the left side of that circle than it is on the right. But on the extruded flat bottom, we have a little bit more of a consistent, it's more, the holes are more, it's more concentric to the outer cylinder. And it's more of a consistent thickness of that material around that hole. Next slide, please. This is a cross section of right at the bottom tips of the impeller blades. And again, you can see a pretty large deviation. You can see the, one of the measurements that were taken on one of the tips there. We have a positive deviation on the top of about 8 thousandths, whereas, oh, I'm sorry, is that 8 thousandths? Yeah, it's 8 thousandths. Almost, 8.5 thousandths, and we're at just about 8 thousandths there. So similar deviation for the extruded flat bottom. Yeah, overall, there's a little bit of a twist in the part. So it's pretty consistent between the two. So here, this was actually interesting because the curved, the file that was printed with the curved bottom, the cone feature of the impeller is actually more. It's pretty much within plus or minus 2,000ths of the original CAD design, as opposed to the extruded flat bottom that's out by on average about a negative 7,000. So it's the cone feature is actually smaller than the print from the original CAD design. What's interesting here is that overall you can see that the part itself is a little bit shorter than the curved bottoms part. So that was an observation that you can see from this section plot here. Actually, if you go back to the previous slide, Sam or Jeff, if you have any comments about that, I feel like there's a lot of bulk material. There's a lot more material for the image that we're seeing on the right for the part that was printed, and just wondering if you had any comments about why it would go a little bit short, perhaps some heat, the way it's cooling, or any particular warpage.
The only thing that I could comment, Sam, here is I'm wondering, if the best fits off just a little bit, if the whole part dropped a little bit, and it's thrown off by the lot of excess material on the bottom. That would be one potential guess. But I also wanted to point out that both parts warped, and it's less noticeable for sure on the extruded flat bottom. But when I was taking the parts out of the machine, the entire build plate itself, which is a 10 by 10 square build plate that's about 14 millimeters thick, 10 inches by 10 inches by 14 millimeters thick. That entire build plate warped significantly to the point where I actually had to drill out a screw to get it out, because the screws were just stripping out as opposed to loosening up. And that contributes to the fact that even though the extruded bottom part was extruded solidly attached to the build plate, it was enough thermal stresses there to actually warp the build plate as well. So it is something to keep in mind. In hindsight, I should have used a thicker build plate. Would have made my life a little bit easier getting the part off. But in either case, warping is part of the process in this case, and it's something that anybody using this process or a comparable process definitely needs to be aware of. And it can be compensated for in some cases, but you don't really know until you try it. But it is certainly an issue that needs to be taken into account.
Yeah, absolutely. Yeah. And as Sam mentioned, I'll just comment really quickly about the compensation. Some of the deviation plots that you're seeing, because we have a holistic mapping of the deviation of the surface, we can go in and adjust the CAD model to have a negative offset of that deviation to then put back into the machine. The plan being that part will now warp into a more into a more conforming shape than previously. Sorry, Jeff, I cut you off there.
No, I was just going to say that the other observation is that these measurements were all as built, so it's not uncommon to stress relieve or do some kind of heat treatment on this. So if it would relax and what the differences are, we should measure in the future as well.
Yeah. Next slide. So we also went ahead and did CT scan. We just wanted to make sure that the passages were clear And if we can take some measurements of the passages. So what you're seeing here is a digital X-ray detector on the left, the part in the center, and a 225 kilovolt X-ray source on the right. We're able to take digital radiography images, so just 2D X-ray images, and we can take some measurements on that. Then we also ran a full CT, which is rotating the part while you're taking, thousands of X-ray images, which then go into a reconstruction to come up with a volume scan of that part, and then that gives you more data to do some more analysis on. So you'll see that in the next slide. So here you can see in the picture on the left, you can actually see the cooling passages on the tips of the impeller blade. A magnified image of that is on the right. So what we're seeing there is we're just verifying that those passages are clear. Next slide, please. And then this is a slice of the CT data. And what we're looking at is the picture on the right is showing the actual measurement of the cooling passages. We're both verifying that the cooling the passage is clear, and just a quick check on the on the diameter of that. Next slide, please. Here, you see them on the tops of the impeller blades. You can see that the diameter is slightly different, but within a pretty close, I think it's about 5,000ths of each other. Next slide, please. And then the wall thickness measurement here that we can take from the CT scan. So again, pretty consistent on the wall thickness as well. Next slide. Again, so wall thickness measurements on the left. You can see that the internal cooling package that goes into that cavity. I can take a measurement on that. And then the diameters of the tip cooling passages there as well. So pretty consistent in terms of the diameters of these holes. Next slide. So we can get into more questions at the end. Just keep in mind that there's a questions panel on the right side of the GoToWebinar. Feel free to type in your questions there, and we'll be sure to get to them when we get to the end here. So as we get into case study number 2, this was done for a company here in Connecticut, ACMT, and this was on a sheet metal bracket part. This was really, as Jeff pointed out, to automate the design of the fixture using generative design software. And the kind of the first step is that we take a look at the part, and unfortunately I couldn't share a screenshot of the drawing of the part. I put a couple of measurements on there that you see on the part there, basically just the datums. And I look at the drawing, I look at the part, I apply the material to the part so that we can do a calculation on the where that center of mass is, which is what the dialog is showing there on the left of the part. So we know the center of mass, its location. You can see the coordinate system that's indicating the center of mass, and the hole at the bottom right of the part is, you can see the XYZ coordinate system there. That's our datum reference. So, datum A is actually the bottom surface of where that mouse was pointing. Then that hole is datum A, and then datum B is the hole on the left. So you see that with the coordinate system there. So if you take fixturing or screwing down datum A, we can take we can calculate the force that particular, that the fixture is going to see based on the weight of the part and the forces that we know that are, the part's going to feel when we're going through and doing the measurement. And the measurement technique here is not non-contact, it's actually a contact measuring with a height gauge. And then there's also I think a secondary step with a ferro arm, so a kind of a portable CMM. Next slide, please. This is a few more screenshots of where that center of mass is located relative to that front right hole that we saw. Next slide, please. So what we're doing now is just generally blocking out the design volume that we're going to present to the generative design software. I want to be able to measure, some key features, and I need to be able to get to it. And so the design volume is constraining the space within which the generative design software can create that fixture. So I'm just defining that. The picture on the right, you can see kind of a cylinder feature, which is acting as a pin for the hole on the right. And then the feature on the left hole is a diamond pin type design to constrain it so it doesn't rotate. And then the bottom surface is going to actually made up against the bottom of that sheet metal part. So you'll see it clear in the next image here. So the picture on the left is, of course, like I mentioned, the design space. And then what we need to do is tell the, define what are the individual components that we can select to tell the generative design software, what's going to be fixed, what features are going to see a loading on it. So the image on the right, you can see are the individual components that we can click on as a body to tell the generative design software that, for example, the 4 holes at the bottom, they're going to be fixed. So we're going to put a screw through it so that this whole fixture is screwed onto a breadboard. And then the part itself is going to made up against that top surface. But the kind of the cylinder feature you see on the top right, that's acting as both a gauge, so that hole slips right over that, and then it has a through hole at the top of that, so that we can actually screw in a 1/4 inch 20 screw to hold down the part. And so we're going to put the loading case on that pin there. So now we import that geometry into the generative design software. We're using Parameters, CogniCAD. And the first thing that we do is we set up, you see the image on the left, we're setting up our material. I took a screenshot when it said stainless steel, but we actually changed it to composite carbon fiber material later. And then the image on the right is showing the selection of the design space. So the the geometry that's highlighted in blue is defining my design space. So I'm telling the software that this is the space within which you can design the fixture. Do not go outside of that, because I'm going to need to access areas of the part. So that's my way of constraining that. So if you hit next, the next slide. So the image on the left is showing now the selection of the non-design features. In other words, what I'm doing here is selecting the 5 components, so the 4 cylinders, which represent the holes at the bottom, and then the flat surface on the top with the diamond and the gauge pin feature at the top there. And then the next step is telling the system that the 4 cylinder features at the bottom, which represent the hole, are going to be fixed. So those are our boundary conditions, and we're going to set those as fixed. So next slide, please. And then the next thing we're going to do is set up our loading on the top face. And the loading is calculated from just the weight of the part and a couple of pounds of force just from the it's actually not going to be a couple of pounds, but we just set it as a couple of pounds of force from the touch, from the height gauge. So you see the moment and the force measurement applied there. And then the image on the right is showing what our design goal is, and we've selected generative design exploration. So what we want to do is maximize the stiffness of the particular fixture. The other option is to optimize it for lightweighting, but in this case we want to optimize for stiffness. Next slide. Here we're looking at what volume of fraction we're going to allow the system to calculate down to. In other words, it's going to reduce the amount of material, and it's only allowed to reduce it down to 30%. It may not get down to 30%. It's depending on the optimization and the stiffness requirement. It may only reduce it to 50%. But here we're just saying that absolutely do not go beyond a reduction past 30%. So that's what we're setting up there. And then on the right side, the image is showing what our manufacturing method is going to be. So is it going to be additive? Is it going to be 3-axis machining or 5-axis machining? We can set that up in this software. When we set it up for additive manufacturing, essentially, a lot of the design constraints are released. We're not with 3-axis milling or 5-axis milling. There's more design constraints put on there, and so the design is kind of constrained to be able to actually produce that part. But in this case, we did it with additive. So next slide, please. And here are the results. So we went ahead and ran that optimization, and this is what the software gave out. So just to let you know, that whole process of some of the screenshots that we went through to set up the generative design software, going from what I use SolidWorks to interrogate the part, that was about a minute. I mean, you import the part, you add the material on, and then you do mass properties, and it just gives you the center of mass. And then I could just take the measurement of the center of mass from whatever reference I want to take, which in my case was the bottom right hole on that part, which was datum B. And I calculated all my forces off of that. So that was about 2 minutes, 2-3 minutes. And then once I blocked out the geometry, which was another couple of minutes, I imported all that into Paramatters, went through the dialogues. It's literally just click and next, click and next. So the overall process was, I think it was 7 minutes and let me see, 7 minutes and 42 seconds. I wrote it down here. So it was very, very streamlined. I didn't necessarily have to go through and think about, how I want to design everything. I just kind of give it the information, and it comes back with a design that I can just send to the printer. So you can see how it optimized the bottom there. It really reduced a lot of the material. You still see quite a bulk of material if you look at the image on the bottom left, on the left, the legs on the right are thicker than the legs on the left. And that's because more of the force is seen on the right, and more of the moment force is towards the back of the part. So if you see the picture on the right where the part is flipped upside down, you can see the bulk of the material is on the back legs, or the back holes that hold up, that are bolted down to the breadboard. Next slide. So in the software, for printing, I could, it outputs an STL format. So I could go ahead and just export that out into the printer software. But I did just want to show, in case other formats are needed, the software can surface the file, and it does this totally automatically. It's literally a button click if I want to export it to a step file. You see that it's not like a traditional CAD model where you have, that top face should be just a one plane, and then the holes should be just a cylinder cutout. So it's not like I can just hover my mouse over the top plane and that whole plane is selected. but instead it patches the surface. So it fits surfaces to the STL file and then outputs that as a step. What that enables me to do is import that into softwares that wouldn't take STL or that work with step files. But just wanted to point out that this is one of the features of the software that you can output. So in our case, we're just outputting the STL file and importing that into our Markforged Eiger software. This is a cloud-based software, so we just upload it online. And in this screenshot, we're just showing overall part details. You can see that on the left. Print time was about 8 hours and 44 minutes. The cost of the material is like $10. And on the right side there, the dialog, we're using the Markforged Onyx material. There's no reinforcement material, but we could use Kevlar, carbon fiber, I think another material that I'm blanking on. And then if you go to the next slide, our layer height is set to 0.1 millimeters. We can go to 0.15 or 0.2 to speed it up. Next slide, please. Here, once we run the slicing, you could see that the purple there is the support material. Inside the part, this is really what I wanted to show, was that we're doing a mesh, like a triangular mesh infill. It's not a solid infill. We're just doing I think a 2-layer wall on the outside. And this is gonna go into further reducing. So some of that was calculated during the when we set up the material in the generative design software. Next slide, please. This is a 3D view of everything. So you can see through the part, you can see the structure on the inside of the part and where all the support material is going to go. Next slide. So this is just setting up the machine. There's a dry box that the Markforged uses because the material absorbs moisture. So we want to keep it dry. You see the Onyx material there. This is the machine. And the picture on the right is showing the part as it's finished building. You can see the support structures extruded down to the build plate. Next slide. A couple images, close-ups of the part as it's on the build plate. Next slide. Again, there on the bottom, you can see how the support structure was built. And then this is the support structure removed. So in this case, it's just, it just peels off pretty easily. So here, what we're doing is, again, we're setting it up in the GOM system to scan it. We're setting it up in the cage. I sprayed it white simply so that you could see it clearer. The material is matte enough where we can scan it. It wasn't a shininess issue. It was more of a just wanted to highlight the part in the system. But what we're doing is we're actually, in this case, we're setting up reference dots on the part itself because I wanted to flip it over and scan it from the bottom as well. And those reference dots are used to align the top and bottom halves. Next slide. And here's the resulting scan. So you can see, the bottom of that part, the image on the right. You can see that as I remove the support material, it creates like a rougher surface on the bottom. So just something that needs to be kept in mind. I could have flipped the whole part over and printed it on its top, so that the top was touching the build plate. But because that top surface is actually mating up against my datum on the sheet metal part, I wanted that to be as clean as possible. So that's why I had it printed the way that it printed it and having all that extra support material. I could have probably minimized the support if I printed it upside down. But again, just taking into account, the cleanliness of the surface that I need and where I need it. Next slide. This is a comparison of the, of the original design compared against the built geometry. So you can see the deviation there on the legs. We have positive on the sidewalls of the on the legs of the part. On the top surface, we're negative, but it's almost it's a consistent negative. We're about just 0.002 under, but it does go into a almost zero deviation. If you look at the picture on the left, the top surface towards the cylinder feature is green. That is indicating nearly zero deviation. But as you get towards the center, you get a little bit more blue, but it stays within the 0.002 range, and then back out to zero. So there is a little bit of curvature on that top surface. The cylinder though came out pretty good, which is our, it's acting as our pin. So it had kind of a slip fit for the hole in the part, and that there you can see is indicated as green. Again, a couple other images. You could see the bottom of the part is mostly positive deviation, but that's okay. It overall indicates that because my top surface is negative and my bottom surface is positive, by a little bit of a different amount. It's not that the thickness is consistent. The thickness, it's a little bit thicker, but it's a little short as well. So just a note there on this particular printer's capability when it's printing up in the Z direction. Next slide. Okay, so some measurements here. So I wanted to make sure that the bottom holes were clear so that we can fit 1/4" 20 screws. And you can see all the dimensions here. So D1, our nominal was 254 thousandths. Our measured value is 251, so just 3 thousandths short. Again, on D2, we're just short by about almost close to 4.5 thousandths. D3, we're short by about 3. So on average, we're about 3 thousandths short on the hole sizes. On the outer cylinder, we are positive by about 3 thousandths. So the takeaway here for me is that there's about a plus or minus 3 thousandths deviation if I use this particular printer to produce these parts. So what I would do to compensate would be to design, go ahead and edit critical features to be either +3 or -3, depending on if they're, ID or OD. Next slide. Measurements of the top feature here. We're actually pretty consistently at about a positive deviation. D11 is an angle measurement, so that's degrees. We're out by 0.27 degrees. But altogether, average, we're at about 3 thousandths positive deviation. Next slide. For our cylinder feature on the left, the outer diameter is out by about 2 thousandths, so that wasn't too bad. And our length measurement on the diamond, we are just short 5 thousandths. It's not positive, which is good, because then it wouldn't fit. And the feature, the cylinder feature that acts as a pin is a +2 thousandths, but you'll see later in the images, the part did still fit on there. It was more of a, it was less of a slip fit, but you can still push the part onto that particular feature. Next slide. And then this is just a cross-section deviation of halfway up the legs of the part. So I just wanted to show that on average, we're about 3,000ths. And it looks like the legs are they're further out than they're supposed to be. But altogether about 3,000ths deviation. So it's pretty consistent in that. Next slide. And here is the part actually on the fixture and being used on the height gauge. So it was stiff enough, and it met the requirement. So for about 7 minutes of work and about 8 hours of print time, the process was fairly automatic. There was not a lot of work that I had to do. I just had to do the setup, and then I could just walk away, concentrate on other things, and then come back to a printed fixture that I can use to fixture down my part for measurement. So that it took away the time that I needed to sit there and manually create that fixture. At this point, I'll invite Jeff and Sam back on, and we'll go through any questions that folks might have for either of these two use cases. Any comments by Jonathan from Concepts NREC?
Yeah, thank you. This is Jonathan here. Yeah, really great presentation and great work. One thing you didn't mention is the timeline you pulled this off. Very short timeline to both build and to inspect that cooled radial turbine. It's pretty important when it comes to product development to not just have a theory, but then to prove it out as you did from a manufacturability perspective. So yeah, I just want to say great support, well done, and really nice to see not only the work done, but lessons learned, right? It's always successful on a timeline, but we learned a lot about the design we submitted and then the resultant hardware that you produced. So thank you all on this team.
Thanks, Jonathan. Yeah, appreciate that. So it looks like we don't have any questions, so we can go ahead and move on to the next slide. So we have opportunities for defense supplier companies to participate in technology demonstrations. If your company has had at least 5% of your sales in one of the last 5 years, that ultimately benefited Department of Defense. We welcome you to apply for these no-cost demonstration projects at ccat.us/Nerdic/apply. These demonstrations, again, as you saw, are intended to be presented publicly. So preferably, we're looking for non-ITAR or export control projects. Otherwise, we can work with you to identify components of the projects that can be recorded and presented. We do currently have additional opportunities for free 60-day trial of artificial intelligence using Stanley X's DeepHow training and upskilling tool. If you are interested, please do apply by August 20th. We have a few, 2 more technology demonstrations coming up over this month on August 17th and 31st from 12:30 to 1:30. The results of the additive manufacturing demonstration projects will be presented by our technology partners at the Berkshire Innovation Center, University of Maine, Center for Additive Manufacturing of Metals, and Vermont Technical College. The presentations on these technology demonstration projects are meant to illustrate real world applications of these technologies, what challenges in manufacturing these technologies help to address, how the technology was applied between the different pilot projects, and what the outcome was. So we do welcome you to register to attend these presentations at ccat.us/Nerdic. We did want to make you aware of this great opportunity for manufacturing companies. The U.S. Air Force desires to expand the U.S. supply chain capacity to manufacture small turbine engine parts. These are engines that produce less than 2,000 pound force of thrust. The goal is to reduce cost and delivery schedules for existing suppliers and stand up additional suppliers, including from non-aerospace industry sectors. We welcome you to visit sep.ccat.us for more information and to apply for consideration for this program. With that, we'd like to thank you for taking the time to join us today. We hope the presentation helped to understand the benefits of additive and generative design. If you do have any further questions, please do feel free to contact us, and we'll be sure to get your questions answered. So thank you again, and have a great rest of your day.